Hi, welcome back. So today we will be learning about cost function, which is a super important topic in machine learning. I would say it's heart of how a machine learns. So let's break it down step by step. So why do we need a cost function? Imagine that you're trying to become the best basketball shooter, and apologies for a really bad graphic, because I am not good at drawing, and every time you take a shot, you either make it or you miss it. To get better, you need to measure how far off you are from making the perfect shots every time, right? So you kind of measure and you're trying to figure out, how far, and then you try to improve accordingly. The cost function in machine learning does something very similar. It measures how far our predictions are from the correct answers. So if you remember from the previous video, our straight line equation, or our best fit line, the equation for it looks like this, right? Where x is our input, which was the house, y is the actual price, and then w is the slope, and b is the bias. But how do we know if our line is good or bad? That's where cost function comes in. So how bad are our predictions? So let's say we're predicting house prices, and we use a formula from our model like we saw earlier to guess the price of the house. But sometimes our guesses are way off, and we need a way to measure these mistakes. This is where cost functions comes in. So let's start with an example. I'm gonna go back to the house example. I have a house size, which is my x. I have the actual price, which is my y. I have the predicted price, which is my y hat, and then I have the error, which is my y minus y hat. And then I have few data points. So I have 1,000 square feet house, which the actual cost for this is 150K. And the predicted price from our model was 140K, so we are off by 10K. Now, similarly, 1,200 square feet house, actual price that it got sold for is 180. Our model predicted 175, so we were off by 500. And then finally, we have this house which got sold for 225, but the predicted price was 230, and then the error is 5,000. So each prediction is off by some amount, right? So the cost function takes all of these errors and then it summarizes them into a single number. And notice how some of the errors are positive and some are negative, and that's gonna come into play later. So let's talk about how we actually calculate this cost. So the most common way is using what's called a mean squared error. Mean squared error, or MSE, right? So the formula for this is, and let me write down the formula, and I'm going to explain each part. It might look really intimidating now, but once you understand each part, you're going to laugh at how simple this is. Okay? It's actually very easy. Okay, it just looks scary. Take a picture, make a note, whatever you want to do with the formula, and let's start breaking it down. I'm going to choose this color. Okay. So our first part, JWB, is our cost function. That's what we're trying to figure out here, and this tells us how good or bad our model is. And then the next part, we have our M right here, which is number of data points. So going back to our house example, it's just basically total number of houses in our data set. Very easy, right? Nothing scary. And for this part right here, HWXI is just my other way of writing the predicted value. So it's basically what our model thinks the price should be, right? We know what predicted values are. Now, our yi is the actual price. for I is the ith value. And then yi is the actual price, the real price of that house. Very simple, right? So when we combine these two and we look at this whole thing, what is hwxi minus yi squared? It is squared error. Like the term, in the term we talked about mean squared error. So we already have the squared error part figured out, right? So now let's go to the mean part, which we have to figure out. So this part right here is what gives us the mean. Our half I equals to 1, m is the mean of all squared errors, which averages out all the mistakes. And why this half, I'm going to come back to this later. So you might be wondering, why are we squaring the errors? Why are we not just adding them up, right? Why is it mean squared error? Why is there a square instead of just simply adding up all these values, right? So number one, no negative errors. So some predictions are too high like we saw here, and then some are too low like we saw here. So if we just add them up, they might eventually just cancel out each other and give us 0, which is misleading because there are errors out there. So squaring makes them all positive. That way we are accounting for all the errors. The second reason is we want to penalize large mistakes, right? So say we have error 3, error minus 5. Which one is a bigger error? Obviously minus 5. So when we square it, this becomes 9 and then this becomes 25. So this is way worse, right? Like 25 is way worse than 9. This is way worse. So what we're doing here is making sure that bigger errors hurt the cost function more, which forces the model to reduce large mistakes. So I hope it's clear. So see, it's not intimidating anymore. As the name suggests, it's just mean squared error. Error we know is our predicted minus actual, and then square is just squaring them, and then mean, we all know what mean is. So simple, right? Now let's go to visualizing the cost function. So let's imagine the cost function as a big hill, or better yet, a bowl. So let me draw that for you. So I'm going to imagine my cost function as a big bowl. And this also makes sense, right? Because we saw this squared value up there. So we were expecting something like that. So the lower we go, the better our model is performing. So the lower we are going, we know our model is performing better. And when our cost function is at 0, then that's our flat ground. So if our predictions are bad, our cost function is high. We're sort of at the top of the hills. But if it's getting better, then we're getting closer and closer to this 0. So if you want to imagine a 3D cost function, it really does look like a bowl with a valley at the lowest point, if that makes sense. Our goal is to get to the bottom of the bowl, which makes the best possible model. Now, okay, so we know how to measure errors here. But how do we reduce them? That's the goal, right? To reduce the errors. How do we move towards the bottom of the goal that I just, not the goal, the bowl that I just talked about? The answer is what we call a gradient descent. So we're getting into really, at least what I think is very interesting topic. So we will be talking about gradient descent. Can I spell today? I think I can. Okay. So gradient descent is basically the learning process. That's why I find it really interesting, because it's the learning process. we start with a random guess for, if we go back to the cost function, our best fit line function, we have this. So we start with guessing random values for our W and our B, because that's the only things we can change, right? We cannot change the X or Y. And then we check the cost function to see how bad it is. We make tiny adjustments to the W and B to lower the cost, and we repeat this until we reach the bottom of the cost function bowl. And in the next video, I will talk more about how we achieve this. So let's recap everything we learned in today's video. So a cost function measures how bad our model's predictions are. We use mean squared error to calculate it. Squaring errors helps because everything becomes positive, and then it penalizes the big mistakes. The cost function looks like a big bowl. Our goal is to find the lowest point, and we use what we call gradient descent to slowly move towards the best values for W and B, which we will be looking more in the next video. Your girl can't speak today, okay?